Guys, good morning. Thanks for coming to the ITS seminar. Today we are It is our pleasure to invite PhD candidate Junyi to give us a talk on the I-24. And
Just move, you're out of the camp. There you go.
yeah, sorry. So my connection with Junyi is that we both work at Northwestern for summer. So I work at Northwestern in the year of 2018, and Junyi worked at Northwestern with Marco in the year of 2019. But he's a distinguished alumni, and I'm just normal alumni. And then so after Junyi finished working with Marco in 2019, he continued his master's degree in Southeast University, one of the best universities in China, especially transportation. And afterwards, Junyi applied to Vanderbilt University, working with Professor Danwork. And Junyi has done amazing work in terms of the test bed, in terms of data, transportation wave. One thing that I noticed about Junyi is that he's very familiar of the history of transportation. Who first did this study? Who first did that? Just the other day, he's showing me that the ISTDT proceedings in the year of 1965. So Junyi is a very productive graduate student. I just checked this morning, Junyi's Google Scholar has 540 citations, which is comparative to which is like an assistant professor, 540, which is 500 more times than I am. So the other day I just read an article that surviving through grad school or thriving through grad school. So I'm the examples of surviving through grad school, and he's the example of thriving through grad school. So let's give us undivided attention to Junyi and see what thriving through grad school look like and what he has for us for the I-24 project. Let's give him a round of applause.
Thank you all. Thank you, Sui. I mean, we have a very nice connection, even though we don't really meet at the same space and time at Northwestern, but we keep the connection. So it's my great honor to be here to discuss with you all about the freeway congestion. So I-24 motion is a testbed is capturing, designed to capture the stop and go wave, which is actually the initial idea of traffic science. So today I'm going to give you an overview about the testbed and how many data sets we have generated, what's the new insights and what it can be done in the time of AI. So let's get started. So before I go deep dive into the congestion and traffic wave, I'm glad to share a bit about my research overview. It's on transportation cyber-physical system. Exactly this week, I come to UCI just to go for the CPS IoT week. So my work is mainly on, first part is the testbed. So I-24 motion is a testbed with 294 cameras trying to capture all these kind of moving vehicles on the freeway. So there are 40 poles in total along the 4-mile section, and each pole have 6 cameras on top of the pole, and each camera is looking at one section of the road, so that you can connect all the cameras together to have a bird's-eye view of the vehicle moving through the corridor. So what's the use of this kind of testbed is actually we can use the testbed to do experiment. So that's a picture, a very nice morning, but it's actually 5 a.m. in the morning. That's a typical experimental morning that we drive the car and connect with the sensors and trying to do some traffic experiment. So these testbeds have enabled multiple impactful experiments, including 2022 100-car experiment to do the traffic smoothing. And after that, we keep doing more experiments, although that's not that impactful as the 100-car, but actually bringing many new insights. For example, last year, October, we did a collaboration with European Commission Joint Research Center to test 6 different kinds of level 3 hands-off car to see what kind of safety regulation we can make for Europe, because those cars are not allowed on the road in Europe, but they are allowed in the US. And then our testbed enabled this kind of test to collect trajectories and reason through what's the safety issues and so on. So the testbed is that's kind of enable the full-scale experimental traffic science. So I would also like talk a little bit more about the origin of the traffic science and so on. So with the testbed, and then testbed are generating huge amount of data. So that's the data we have collected since 2022. It's here now it's already about 200 days of the data and sum up to be 20 billion of trajectory data points. You can imagine a camera capture a car, and that's a trajectory point in the space and time. So I developed some tools to automatically quantify these kind of congestion features and the properties, and it actually reveals the complexity of the traffic waves. So now this is all about traffic physics.
Okay, I have one question. I mean, for this I-24, actually, I checked the the map. I'm wondering if this is to the northwest side or the southeast side.
Of I-24.
Yeah, I-24, which stretch you guys have camera on.
Okay, so
It's on the Nashville, right?
to Nashville.
Yeah.
That's from Memphisboro to Nashville. Okay, I think I should get a better map.
I mean, or Clarksville, from Clarksville, or because I see the traffic is very directional. Seems like major corridor. Connecting.
Yes, it's a corridor connect a city Memphisboro to Nashville. That's probably if you try to search
Murfreesboro. So
Murfreesboro.
Okay, so that is the southeast. Southeast.
Yeah.
Okay, thank you.
Yeah. So that's a location of the testbed, and it's the most congested corridor in around Nashville, because not just the daily commuters, but also like FedEx based at Memphis. There are a lot of trunks, and I will show you some videos about how many trunks are blocking the lane on 3 and lane 4. So with this kind of data, it's good to understand the traffic physics, but nowadays, like people are more and more interested about AI, but are the traffic data AI ready to do something amazing? So we take these kind of 200 days of data and come up with idea like, what about do the super resolution? It's like super resolution is more like you take a photo from 50 years ago and plug in the algorithm to refine the resolution. What can we bring in the same idea to traffic data? But most of the time, people don't have the ground truth. But our testbed provide a ground like to this kind of AI-ready data set to facilitate AI application. So you can see like that's a conventional sensor. It's like radar sensor or loop detector aggregated over 30 seconds, and the spatial interval is about 1 mile. And then we see that some early preliminary results, like it looks like reconstructed wave pretty well. And we know that we build up the testbed, collect data, understand the dynamics. What's the next? Is actually we can do like system operation and control. So here is a overview of how this kind of operation and control we are managing in real time on I-24, that kind of section corridor, Memphisboro to Nashville. So we leverage the existing sensor, which is a radar sensor, gives you the lane level, occupancy speed, and volume, so that we can do many different applications. For example, the variable limit speed control. So as you can see here, the speed limits are changing dynamically. That's my colleagues' work. They plug in some multi-agent reinforcement learning to do this kind of speed recommendation. What I did with this kind of infrastructure is to use the data to do the real-time incident detection. So it's actually also some stories or insights we learn from the data and dynamics from the wave. It's actually the wave can tell you when and where the crash happens. So we will go through the details in the next 30 minutes. So that's just an overview of my current research. Okay, and finally, so not all the university and the state or all the country have this kind of facility and infrastructure to do this kind of research. So I think that reproducible research is actually more and more important. If people share the data and share the tools, so like the new students don't have to build everything from scratch. In transportation research community, we are formulating a volunteer organization. It's a reproducible research rewrite. It's like encouraging people to share data and code and teach people how to share data and code. So actually this Tuesday morning, we organized a tutorial at the CPS week to teach people how to like make your code just a step away to be public. Like the trajectory data is also international, currently international attention from multiple groups. So we initiated a trajectory data camp, which like last year we at Edmonton, the topic is bridging traffic and vehicle research, and this year at Australia, that's our topic is safety and the human factor. So the idea is not just to do something by ourselves, but open the floor for everybody to use the data and accelerate the transportation research. So that's my vision for the next 25 years of transportation research. So let's go to the traffic wave, which is the main point of today's talk. So allow me to give you a brief history of the traffic congestion, how people capture traffic congestion. So how many of you have heard about this ring experiment done in Japan? I believe many of you have heard about that. So it's like, but actually that's not the first ring experiment. The first ring experiment is done in 1950s in England. That's a road research lab led by Smad. That he actually did a ring experiment in 50s, and they even did some traffic smooth control. So you can see here the fundamental diagram, that's the density and the flow. And there is a point, looks very nice because the density is increased and the flow are kept. So they did some very interesting control strategy that, think about that's 50. So they have a person standing next to the ring and observe the traffic. And if the person realizes there is a slowdown in front, then he starts to wave his hands to the drivers to inform them to be careful. And then they get this point. So that's actually the ring experiment is initiated even like 50 years ago. So that's very amazing. But that's how people trying to understand traffic congestion do controlled experiment to see how traffic looks like, especially in the transition from free flow to congestion. So then it's like in 1960s, there is a famous engineer, Edie. He is the director of the New York Port Authority. It's like the New York Department of Transportation. So they figured out a very practical engineering problem. So Lincoln Tunnel and Holland Tunnel usually only get a capacity of 2,000, but another tunnel usually get a 2,700. So they are thinking about what about the congestion really looks like. So, and actually they capture, I think that's the world's first time-space diagram. They use some like a camera device and some pulse incentive sensor on the road. So if a vehicle goes through this kind of powers-based sensor like loop detector, like send a signal and then the camera starts to capture and then calculate the speed. So the idea is if there is a car and they capture one and estimate speed and put in the space-time diagram. That's, I believe, the first time people really understand that the traffic wave can propagate in real world setting. And later on, based on their findings, Edie and Garces, they did some experiment in the Lincoln Tunnel. The idea is, what about we like try to control the flow coming into the tunnel, and can we really improve the throughput and so on? So their experiment. Again, that's 60s. That's the first application of IBM computer actually in real control system. And they found that there are 12% of increase of throughput. And that's a very early success of traffic control. And one more thing is very interesting. I found in one of the paper written by Newell, he mentioned that actually the benefit from traffic smoothing control not come from the increasing throughput, but come from the increasing the exhaust emissions. So you guess how these kind of research projects are funded at that time. So basically it is funded by the electricity save. It's like for these tunnels, if congestion in the tunnel, then the combustion have the exhaust emissions and accumulate in the tunnel. And then the tunnel have to use the fans to make those kind of emissions out. Then the electricity itself in the savings can compensate for all these kind of investment on the digital controllers and so on. And not to mention that's ISTTT bring this kind of expert together. And another famous professor later working at UC Berkeley, Professor May, he visited Edie's lab and take this idea to Chicago Authority and then deploy the world's first ramp metering in Chicago. And he's the one who invents the light control for the ramp. And then the director of California Department of Transportation at the same seminar brings this idea to the Bay Bridge. So basically, the words, all the traffic control comes from that, like from experimental study, empirical study, and empirical control. I spend much time to talk about this. It's like that's some idea and philosophy I'm practicing, like trying to do bring this kind of thing back in nowadays. So another data set that people collect in the 60s is that they use helicopter. So it is actually a very nice data, but not used frequently as often as NGSIM. So it's a data set collected by Trifler in 1969. So this data is sleeping in the library of Ohio State University. And it's actually a full mile section of freeway and about 5 minutes. It's not as good as NGSIM in covering the time, but the spatial coverage is way better than NGSIM. And again, that's based on the camera technology in that days. So in about 2018, Professor Kaufman, he's still working at OSU and visited the library and scanned the book and then digitize all the trajectory points. So now everybody can actually download this data and do all the analysis as we do for NGSIM and so on. But it's some idea like people's efforts from 80s, 60s to collect data. So the idea is like keep growing up, and in 2000, the NGSIM started to become the golden standard for the data set in transportation. And stop and go wave is actually around the world everywhere. So you can see here, there are data sets collected by in Germany by Dirk Helbing and Atlanta. These are the famous videos showing the stop and go wave. It's a global challenge that everywhere around the world have the stop and go wave. And I also like a fan of this kind of phantom jam, and I hang up a camera on top of a very high building and trying to capture some stop and go wave at my undergrad and master's time. And that's some stop and go wave I captured. It's also very interesting. And then that's my time to decide which PhD program I want to go for. Then I start to browse the information and find, okay, there is a project at the Tennessee called Items for Motion, which is capable to capture everything. So in 2022, I moved to Vanderbilt University and started working on this project. So it's a 276 camera on the main system. The extra 18 cameras are the first validation system. So it's like have the 4K video data about 1 gigabyte per hour. So it's like you can have an overview of how many cameras or system are composed of, and you can try to track the vehicle by your eyes. But we did that by the computer vision algorithm. And then you can get so it's like a typical civil engineering project. You need like hard work people to build up all the infrastructure and deal with many uncertainties. So that's a civil part. And then here we go. We make the all infrastructure both digital and civil, like physical, down, and then generate the space-time diagram, the trajectory data, like the NGSIM data. So here it is the size of the NGSIM size, and the background is our data size. And you can clearly see if we like this kind of data, not just to capture trajectories, it can also like overlay your own vehicle trajectory over the space-time diagram. So you can see here all the white trajectories are the controlled vehicles moving through the corridor. And then you can try to understand what's the interaction with all the cars with the wave, which is like not really think about before. And with this kind of data collected, we released all of them once our paper is accepted. So in October 2023, the data.
Could you please go back to the early one? What are those white stripes?
So the white are the experimental data from the controlled vehicle. So that's the 100-car experiment. So we overlay the vehicle data, the trajectory data collect from vehicle, and the data collect from infrastructure on the same diagram. And that's how you can try to see each vehicle, how the vehicle interact with the wave.
And just to be clear with this visualization, the red stripes are the traffic waves that you were talking about, the stop waves?
These are the traffic wave. The red ones are the traffic wave, and the white ones are the individual trajectories.
Got it. Okay.
So it's like the particle and the wave. So the white are the trajectory of the particle, and these are the trajectory of the wave.
Okay.
Yeah.
So for the, this test people floating car, I don't know what you guys call it. And do you guys use GPS or some?
Yes,
other
I think
devices?
I think the data shown here are the GPS data.
GPS, how accurate they are, or they're.
Yes. So GPS data have the uncertainty in the locations. So here we haven't done the cross validation, but we do share 1 hour of the video data that my colleague Derek Laudmans, he manually labeled the GPS data back to the computer, back to the camera system. So that's a data set is also open that have the GPS data matched back to the same coordination system. GPS data is actually quite sensitive in some sense. The error cannot even be really bounded or measured, so it's a lot of uncertainty.
Right. I'm wondering, did you guys consider to have a more advanced differential GPS or what a kinematic GPS? Or, those kind of much more accurate GPS technology?
I think we have one of them in the lab.
It's just one.
Yes.
Okay, not all the cars.
No.
Oh, okay, good.
That's what I understand. So those are just the commercial, not very expensive one, just
Why some of the white, the white card just break?
the white dot, I think just either take over, like the driver take over the controller, or it's like so you can imagine that ACC, your car is running at ACC stat, and if the driver take over the control, then I think that's the label here.
Yeah, but there's some white curve that they just stopped, didn't go upward.
Which one are you mentioning? For example, this one.
The exit.
They are exit the freeway.
Exit.
How many exit ramping?
I think there are, so in the geometry of the freeway of our test bed, there are about 3 exit and 3 entrance, and so like which also like have the 3 this kind of on ramp and off ramp area. So that's the geometry of the test bed. Okay, so so in 2022 we mainly made this kind of rush up to make this test bed online to support the 100-car test, but we also have the data collected about 10 days after the experiment. So all these data are open source, then you can download them and play with them. So there are a lot of limitations of this version of dataset. For example, the trajectory data are fragmented and so on. But still, it can be used for something that we try to quantify the congestion. Because you can, by our human eyes, you can clearly see these kind of wave patterns. So we did some so back to this slide, it's like 4 lanes overlapped together. So the first step we look at the data is that what about we separate to different lanes? So here is some visualization we did with the speed macroscopic speed field, which is at the resolution at 4 seconds and 30 meters. But still it has all this kind of congestion structures. So you can keep an eye on the slide. That's the lane 1 and lane 2 and lane 3 and lane 4. So it's a little bit counterintuitive that the lane 1 actually have the most severe congestion, which is supposed to be the HOV lane.
So is it eastbound or westbound?
Oh, that's westbound.
Westbound.
Westbound is the direction go to the downtown.
Yeah.
So it's really funny. It's like people think HOV lane should have a better priority or better traffic travel time or so on. But from the data, it tells you that actually like the wave is way better in the lane 4 and lane 3. So then the question is that we are able to observe all the wave, but can we measure them? It's like, can we have a way to automatically measure all the properties? So talk about a wave, we usually talk about what's a wave frequency, what's a wave traverse speed, what's a wave length, and so on. So then it becomes a question. So I think just a very brief overview of the space-time diagram is like a vehicle moving across the space and time and drop a lot of trajectory points. And that's how the scale of the problem looks like for a different data set. And we are actually dealing with the most, like the largest scale of the data set across the last 20 years. Then, so the first question is that the scale is a problem and the definition is also a problem. So in the literature, there is not really a clear definition of what is a wave. Then we go back to the history and borrow the intelligence from Edie. Like in his first paper on stop and go wave, which published on 1943, he defined the stop and go wave just like a contour. So have all the speed dropped on the space-time diagram and try to connect the dots with the same speed. We bring the same idea, formulate as a research problem that given a space-time diagram as above and a critical speed, saying 20 miles per hour or 50 miles per hour, can you identify all the wave boundaries? And that's the results we get is quite good because it separates out each wave by wave so that you can have a boundary of the wave, then you can take a closer look at what's inside. So the technique behind is that quite simple. So the detection is that we define if the car going down from high speed to low speed, drop a dot saying that's wave front. Then if leave the slow region, then leave another dot called wave tails. Then you're like trying to have multiple trajectories and do the same thing. So again, the trajectory in the data is not perfect. So it's like have a fragmented issue. We here bring in the idea of virtual trajectories. Virtual trajectory is like you have a speed field and you solve a very basic ODE to like simulate a particle moving across this kind of speed field and still leave a lot of dots on the trajectory on the space-time diagram. And then like we first have multiple wave fronts and wave tails dropped on the space-time diagram. And then we connect the next task is that can you connect them together? So here the idea is also very simple. So if there is a car, like have the wave front and wave tail belong to the same car, like okay, then we are friends. We connect with each other. And if the next car is wave front or wave tails or in this kind of small search region, then we say we make another edge. And then the problem becomes like search for the graph component in these graph problems. And then you can separate this kind of thing out. Like, for example, this is a mini demo, like this component 1 and component 2 are separate out with each other because they don't have connection, either for the wave front to tail or the wave front to front. So that's the technique we develop. And that's how these kind of results look like. All the white dots are these kind of critical spatial temporal points. And we first connect all the wave fronts. And you can see how the wave fronts leave the trajectory on the space-time diagram and how the wave tails leave the trajectory on the space-time diagram and then connect them together to become the wave components. It's really not very hard technique or rigorous, but it works. Then we can have all these kind of results detected. We can reason through what's the wave traverse speed, because you can simply define the speed as the first dot and the last dot and calculate the slope, or what's the traverse distance, traverse time, topology, and when and where the bifurcation and merge happens. So actually the bifurcation and merge are something we find really interesting. Because think about you throw a stone in the water and then the waves start to propagate, but unless they hit another stone, then they bifurcate. So usually the wave is stable. And in the last 20 years or 80 years, everybody assumed that traffic wave is also stable. But you look at the details, they are not stable. It's like a nonlinear and unstable wave that can bifurcate and merge back. Here are some interesting stuff like the wave delta in the wave. So how to understand this kind of thing? Honestly, I don't have answer, but I can give you some driving example. So it's like a driver is sitting in the stopped traffic, and the car in front already start to speed up, but the driver was looking at his phone. And then the gap is opened, and he thinks that he can speed up, but soon, like in maybe 5 seconds later, he have to slow down again. So that's how this kind of wave delta are formulated. Again, I don't have the quantitative measurement. That's some future work. We need to take a closer look at the data. But
I have one question. Do you have a merge or diverge here? Because, you are trying to explain this bifurcation merge, with the spontaneous driving behavior. Very likely, I mean, many times if we have merge diverge and people change the length, they can, create new waves, new lengths. So how do you differentiate this different behavior?
It's a very good question. I don't have clear answer, but I did a distribution analysis of all the bifurcation and the merge point on the spatial distribution. So it's actually not quite close. Yes.
Merge, diverge, those kind of behavior.
It's hard to give this strong conclusion, but it actually happens at those areas without any ramps. So it's like with higher frequency. I can try to find a backup slide, but we did some spatial distribution analysis, but it cannot come to a conclusion saying it's solely triggered by this and that.
Right.
So the conclusion I can say that this kind of bifurcation and merge are not only triggered by geometry change. So that's the conclusion here.
Yeah, definitely that's true.
And then people can start to look at how beautiful the wave is. So this is one day of the wave topology, and lane 1, lane 2, lane 3, lane 4. We have a very brief overview about the visualization, but now you can quantify them. That's how it looks like in different lanes. And we also do some topology clusters. So how many times a wave component bifurcate and merge back again, how many times? And then we did a very simple clustering. So here is how long the wave traverses, and this is the axis how many bifurcated happens. So it actually can some wave no bifurcation but can traverse different lengths, and some wave traverse 4 miles, but again some can be very simple like this one, no bifurcation and merge. But some can be somehow complicated if it's multiple bifurcation and merge, and some can be extremely complicated. So again, I don't have a theoretic explanation for all the phenomena, just very amazing. So I decided to put on the website to make everybody to browse, don't have to deal with the 10 gigabytes data set. So it's a website everybody can browse. It's a gallery of traffic wave dynamics. So if you scan the QR code, that's a traffic waves.github.io. You can click on all these kind of points and see the exact geometry of the wave. So that's what the data tell us at higher resolution and higher spatial temporal coverage. Then we are happy. But what's next? As a research group, we need to survive and keep getting funding. So at the year of 2024, we reached a point that, so basically the first data is generated in 2022. And in 2023, we are revised a lot of system testing and architecture programs, because basically the first launch of the system is a very rush sprint for the experiment. And then we take a year to revise the system. And in 2024, what about make the system next step? So there is a trade-off between quantity and quality. So in quality, definitely we can improve the trajectory data quality, to support more microscopic research, calibrating car-following model and so on. But for quantity, it's also amazing that you can have a daily data collection. So that's what we decide to go for 2024. And ideally, we want both. So that's something we are going to work in this year for quality. Then it's how a day of the daily operation looks like. It's think about it's 24 hours. And so at about 8 a.m., then we get a first coffee and start to visualization and check the data collected from yesterday. And start to record the data from today. And then we get a second coffee and archive all the data to the database, and start the system to do the homography generation, to generate the coordination, and then do detection and tracking. So basically, the challenge for this system, it has to be all the computation have to be finished in a day so that we can have the next day data coming in. But that's how a day of the working looks like. But how a day of the traffic looks like from the camera's perspective. So it's one of the day with a help truck, with a crash and the help truck coming in. And you can see from the very early of the video recordings and how the congestion comes and the sun arised, and also the poles are shaking is head. It's like a sunflower effect because the temperature difference from the standstill are different, then the poles start to look around. That's all the technical challenge and the very dirty details of the project. And then it's like you can browse. There was a help truck in the center, I think, like block the flow, but that's how a day looks like in the camera. Okay, but how a day looks like in the processing system. So it's a multi-node of the computational system, like recording, processing, and putting them together. So each node are taking care of about 3 poles and 18 cameras. And some nodes are processing fast and some nodes are processing slow. That's how like a 4,500 acceleration of the processing. It's like gradually generating all the trajectories, and putting them in the space-time diagram. So now you have an idea of how a day of our group look like, and how a day of the camera look like, and how a day of the system look like. Then we start to think about how about this kind of daily data can really help research. So we are going to release this data set this year, which is composed of 50 days of data and 4 hours per day. So actually you can see a lot of interesting patterns from the daily data collections. For example, here, it's a very sad example, like actually a very severe crash happens and all the lanes are blocked, then no cars are traveling across this point. And you can also like think about why does this happen? It's because like the downstream have very severe crashes and have this kind of making everything to be a parking lot. But this kind of pattern are consistently, like the traffic wave speed are very consistent. So then we take a step back to think about how the traffic state measurement looks like today by different tech company. So here is the INRIX data looks like in the spatial temporal resolution. It's like a blurred version of the space-time diagram. And this is the radar sensor detector. It's equivalent to the PAMS data. I'm not saying PAMS data is like, it's a legend, but this data is like, we will calibrate all the sensor and have the 30 seconds aggregation again. This looks better than PAMS, but still it's not as good as what we see in the motion system. Then we want to think about, in the time of AI, like what's the main goal of our collecting the data? It's actually, we want to do something like ImageNet in computer science. So the idea of ImageNet starts from 2007, and it takes 5 years to have the AlexNet, which changed everything. So we hope that our data set can be the same, can have the same experience, because idea comes from 2017, and the first data set comes out in 2023, and we wish that everybody can use the data to do your own interesting stuff, and then to make this kind of growing of the traffic state estimation. So I think our data can bring in some opportunities that are quite special, because tech giants don't have access to this kind of data, and they don't, obviously, they don't have the interest to collect this kind of data. And it's also a physical dynamic social system, because each drivers are heterogeneous, very totally different from the other fluid dynamics, and with critical characteristics that stop and go wave. And we think that it can help the like ask what traffic can do for AI to like deal with the real world problems. So the research questions we are formulating here is the super resolution. So that's a radar sensor detector data with a 0.3 Meyer spatial resolution and 30 seconds temporal resolution. And we want to see, can we do something to generate the resolution as the right? So that's how the legendary NGSIM data size looks like, and the first release, and the different size of the comparison. And the overview of the results. So in the right part, that's actually refined by a generative AI technique we trained on the data set. It looks like reconstruct the the wave pretty good, and it can be helpful to traffic management center to have an idea when and where the traffic wave are now. So the technique behind is like, so from high resolution to low resolution is an aggregation problem. You can understand as a forward problem, but the inverse problem is quite open. It can be done by reconstruction, by interpretation, by estimation, but still, to the best of my knowledge, I haven't seen a problem to do this kind of upsampling of the original sensor resolution. So the technique here is a conditional diffusion model. It's like we generate the high resolution sample conditioned on the conventional sensor data. There are a lot of details in the technique we can discuss in the Q&A session, but the idea is like try to add noise to the original data to be the purely Gaussian noise. And then when you do the inference, or to have the input, want to have the output, you just start from the Gaussian noise conditioned on the conventional data and keep refinement, and finally get to the high resolution version. So that's the technique is a UNet we train on with a huge model and 2 GPUs. So I mentioned here it's a large model. I think I'm not a smart person because we just try to have a large model, see what happens. So future work can be like, what's a balance between the model size and the results performance? Well, we haven't done this yet, but since we will open the data, we encourage everybody to take a look at what's the best design of this algorithm. But it can be a new benchmark problem in the community. So the improvement we get is like, so we compared multiple methods. One is the ASM, the adaptive smoothing method proposed by Professor Martin Treiber and Helbing at Europe. Actually, we also leverage the ASM to be one of the this part upsampling. So from this data to the beginning point to the condition, we use the ASM as the upsampling part. And so you can understand our result is starting from ASM and keep refine the details that ASM cannot do. So the result is quite okay, that have about 40% of improvement on the Weierstrass distance. It's a measurement to quantify the difference from two distributions. So if you are familiar with traffic sensors and familiar with the relationship of a spatial temporal average speed and the spatial temporal average speed, so usually all the sensors will overestimate the speed. It's like radar sensor, loop detector cannot really capture the speed under 5 miles per hour pretty good. But with this kind of technique, we can shift the distribution and match it to the original ground truth. So we talk a lot about how it can be better understand traffic congestion, how it can be done for AI. And this year we realize it's also a lot of hidden congestion, hidden safety issues in the congestion. So here is a video that shows you how a congestion can finally turn into a crash. So you can see like this lane already in congestion, and this car just hit the car in front. That's a very, looks very easy task to slow down, but people do not do it pretty well.
Where at? Which lane?
Sorry, let me play this again.
All the way across.
You can take a look at this area.
Yeah.
Oh, just hit it.
Then it was blurred to
Got it. Sorry.
protect PII.
Yes.
Oh, so can people actually see PII here at all from this kind of image? In reality, maybe we can, I mean, if zoom in, can see the license plate or anything.
Oh, we can. I think you cannot. We turn down the resolution of the image.
Okay.
You cannot. That's IRB required. Okay, so then we go back to the space-time diagram. Like it becomes a question of, can you find a crash in the space-time diagram? So here is one, it's like triggered by the wave. Here is another one, and actually this one is hard to find, but if you zoom in and you will find it. And this. So this day is like the June 4th of 2024. It actually have 1, 2, 3, 4, 5, 6 crashes in the morning, which create. So the story is that you start a chain reaction of driver instability, and then start a wave growing up, bifurcate when for dynamics and so on, and then it finally makes a particle crash with each other. And like it's the imperfect of the driving behavior then creates a huge chain of mistakes.
So this is 4 hour time period.
Yes.
Oh, so during the 4 hours, there are 7 or 6
Yes.
accidents
Yeah.
happening.
Wow.
It's actually crazy.
Yeah, it's not so rare. I thought.
And then like those are some easy identified crashes. Like, can you find one here? It looks no crashes, and exactly either police report or traffic management center did not accept any incident report, but we found one. So it's hidden here. It's like 2 cars hit with each other and go to the shoulder and check with each other soon and leave. But also still have a bit impact on the traffic.
Where is it in the that part?
It's here.
How did you find this?
So my colleague Derek Loudmans, our lab members are so familiar to read this kind of diagram, and we have a huge video wall in the lab, and we zoom in to browse like, is there anything wrong? So ideally, if you find something like stopped, it's usually something wrong. Then we have access to the raw video data, and we have the IRB training and so on that do the manual checking of everything.
So what you mentioned that in the sensors, there are many overlapping trajectories within the sensors, but how can you tell this is just overlapping or accident?
I think because these cars are stopped,
Or stopped?
then there are videos stored in our database. Then we click on that video to watch from the beginning. So it's not automatic; it's manual.
Talking about shoulder length, do you guys have, the longitudinal, position coordinates? Do you guys also have?
Have the ladder.
Lateral.
Have the ladder.
So, from that, maybe that is one sign, if you can detect they are on the shoulder length.
Yeah, that makes sense. Yep. And there are some other like crashes, a lot of crashes. And one interesting part is that what's going on here. It's totally different from the other patterns. What's going on here? It's like
Is this somebody driving on the shoulder?
No, it's a 4-lane overlapped trajectory data visualization. What's going on here? It's like the black, basically nobody drive, maybe a
Police car, no,
very close.
Emergency vehicle, yes.
construction ambulance or.
That's a rolling roadblock.
Oh.
Yeah. So you have like 3 help truck moving together on the freeway to do some maintenance and so on. But still it trigger waves. So that's very interesting because like in traffic theory, people think that's moving bottleneck or something like that. So it's actually also provides some opportunity to see how a moving bottleneck can create like congestions. It's actually also some wave patterns, but still there's something hidden in the data. So after the lessons we learned from the data, it's actually we can build up an incident detection system which use the knowledge of wave because it's a normal day. But here is a visualization of the radar sensor, like the loop detector system. And if you reconstruct it carefully, you can get this kind of wave pattern as well. But if the wave pattern is blocked, then it's clearly a crash. And everybody can tell here, this space and time is a crash. That's how a traffic wave can also help with incident detection. So it can now it's like become a standard benchmark problems. Can we tell the algorithm to find this point as soon as possible? So the current practice in traffic management center is that 3 officers sitting in the video wall and 8 hours per day in rotations to cover the 24 hours to try to monitor this. So we did a 1 month quantification of this kind of gap. So when the crash happens and when it gets responded. So on average, it's 8 minutes. So it's done by a human and still 8 minutes gap. So the loop is that somebody can if you remember that video, people have crashes, like they start to get off the car and talk with each other and like call the police, like what's going on and so on. And the police usually have to die in the traffic management center to do the communication and then send cars. But what if we use this kind of data sensor to detect this as soon as possible? So we build up a benchmark and dataset paper, submit to NeurIPS. It's actually initially we don't know what's going on in NeurIPS, but one of the professor at Vanderbilt computer science, he suggests us to have a try because you have real data and real incident, and people in computer science will be interested in this kind of how these kind of programs works. So it is we submit this paper and accepted at the NeurIPS dataset and benchmark track, and the performance is okay. Looks like have a 1/4 alarm rate and 2 missed events for 20 incidents per week. But should we just be happy with the offline testing and go out to tell TMC, okay, that's ready to go? Actually not. So but before we go to the real-time implementation, these are some techniques we develop. So we basically model the traffic as a graph. So each LAN and each sensor are connected with each other as a graph, and you can see the wave or propagate across this graph. And we do the graph autoencoder reconstruction, basically put the graph into a latent space and put it back to the reconstructed one to use the reconstructed arrow to detect the crash. You set up a threshold and determine like is that anomaly or not. So like also it's a demo we did at the CPS IoT week yesterday. So we connected the real-time data from the traffic management center and connect to different algorithm. And if 3 of the algorithm vote to agree there is anomaly, then we put a dot on the space-time diagram saying that's alarm. But it looks good in our offline testing, but not that good in the online testing, which is like the deployment. So you can clearly see here are a lot of purple dots here are clearly false alarm. That's because our data is trained on the data collected 6 months ago. But this spring, a hurricane hit the freeway and one of the radar sensors was shifted. So radar sensor is not like loop detector is under the freeway, it's hang on the pole, and the strong wind just make it shifted, and the distribution of the data also be shifted. And then it's like also shows how fragile some machine learning algorithm is. So we open up this kind of testing environment not to say our methods are perfect, but in the other direction, we want to provide a testing environment for people to test what's going on, what's wrong with the model, so that we can keep iterating on the model. Since our data and the code are open available, which means everybody around the world can train their own algorithm and publish on GitHub or Hugging Face, then we can help them to plug in the real-time data, which they don't have access to, and testing which is better. Because this can save a lot of money and fatality on the crash across the state. Final thing is that I want to mention, like, how do we accelerate transportation research? I think open science is a solution. The open science is about opening up more resources for more people to do the research. I can imagine like I have a friend at Michigan that they working on the MCD testbed, and which is like also not everybody can have access to. We are working on a Freeway testbed, but what about we share all our resources for people to testing virtually so that they can do the same amazing job as the people stay on site do. And another way is like open science about sharing knowledge to help more people. So I think it's like a call for everybody to embrace the open science before it's too late. We actually did something with the reproducible research volunteer working group. Like at CPS week, we organized a code tutorial, like trying to help you how to make your code better to be readable and reusable by the others. And we also did a vehicle trajectory data camp to call different people, like people collecting the TGSIM data and European or open ACC data and so on, to cluster them together to discuss what's the next for the data collection and the sharing. So I think it's the future of transportation research. If like we can contribute something to the community, which means the others can jump in and use our code and the data to develop further. So a funny story to share is that actually we should also think about what's the future of publication. So in about 400 years ago, like people want to claim a scientific discovery, they need to document every single detail of the experimental setting. For example, you prove the Earth is round, and you have to report all the experimental setting and so on, so that people can trust your results. And the beginning in last century, all the papers look like introduction, methodology, results, and discussion. But what about now? What about now we are in the time of so-called AI? Because I believe many of the young generations are using AI to help them read papers and doing so on. So I think the way we write paper will also be changed. It will be like you publish a paper with a plot and then with the data and the code associated with, so that either machine can understand and people can reproduce your work as soon as possible, so that we can like accelerate the transportation research for the future. It's like a very complicated problem, and I still enjoy it. So I want to push this kind of thing. Finally, thanks to all the collaborators and contributors, you can see this is our item for motion team. Once we organizing a workshop at TRB, a person from a tech company asked us like, how many people do you have to operating this system? We asked like, guess how many? Like he said, maybe 25. So actually we only have 5 people to operating the giant system. So if you could give us any feedback, like how we can improve and make it an open community, we can try our best to improve the data quality and quantity and so on, so that the community can have a better data to share. Thank you all. I'm happy to take any questions if you have.
Very impressive talk. A good talk assigned is getting people excited. After hearing Junyi's talk, I'm pretty excited about traffic wave, even though I don't know much about it. So let's open up to questions. Do you have any questions, comments, and thoughts?
Yeah, can I?
Okay, so go ahead.
Yeah.
Can I have 2 questions?
Yeah, for sure.
Firstly, I want to ask about, you say that you mentioned the HOV lane is the most congested. So do you have any idea why HOV lane is more congested? My thinking is that because there's only one lane there.
Yeah.
So if the one vehicle goes slowly, it can be more like a moving bottleneck, as you described before. So that can be one of the reasons, I guess. So I'm kind of wondering if you have any reason for this kind of reason. And the second question is that, because you check all of the like data day to day, so do you think that the traffic patterns kind of consistent over days, or like because like Monday, Tuesday, Wednesday, they show some similar patterns over the days, or
Okay. So about the first question, I think it's related to driving behavior. So the wave, the reason why wave is generated is come from the driver instability. I believe all the drivers on HOV lane have higher expected speed. So then this kind of oscillation of the wave become larger than the others. And also cars on the first lane, the engine performance is different from the others. Like think about the heavy trunk, it cannot accelerate and decelerate as aggressive as some small cars. So that's some intuition on that, but I haven't done the empirical validation. It will be interesting to read and through why this kind of thing happens. But from the empirical observation, you can see the difference. So, but I think there's an open question. Or when and where does it really generate it is also an open question. So for the second question, I think it's about what's the pattern different day to day. So I think I can show you the calendar of the data, and also the calendar is already visible in our website, itemformotion.org/data. So here we have a larger version. Yeah. So that's Monday, Tuesday, Wednesday, Thursday, and Friday. So usually the wave have more wave on Wednesday. But I assume people would stay at home or work from home on Monday and Friday. So usually you can see the Friday wave is not that severe. And also there are some other factors could impact the pattern, for example, the weather. So like if it rains, then people will drive more careful, and then but the question is that it will be more or less, I don't know. So, but it provides a ground for you to check and compare. So Monday, Tuesday, Wednesday, Thursday, and Friday.
Thank you.
Two questions?
Sorry?
Did you have two questions?
Yeah, I did have to catch this, yeah.
The answer.
Am I,
I have, well, you can go ahead, please.
you're gonna, I have quite a lot of questions I can say.
I'm not a traffic flow person or a traffic control person. I'm wondering about the kind of practical value of this inverse problem you're solving.
Uh-huh,
Can you
uh-huh.
kind of walk me through
Yeah.
where it could be used.
I think the inverse problem is quite interesting. So in transportation, we have a lot of aggregation and de-aggregation problem. I think this general technical framework has the potential to deal with that. So I would recommend some papers on people did in physics. They also have similar problems, aggregation and de-aggregation. So some current practice is trying to use the conditional diffusion model, which is the same technology we used here. So it's like condition on the, I would say it's more like condition on the boundary condition and generate the thing inside the boundary.
Yeah, you're describing like a technical problem. I'm saying like for traffic.
Oh, yeah.
Why do we want to go from, okay, I understand in the general case, like why you'd want to go from aggregate to disaggregate, that's good. But like, if we train on the I-24.
Yep.
Can we apply this to the 101, the 405,
Oh.
the 95?
Yeah, that's a good question. And I did some testing. So I-24 only cover 4 mile of motion, only the testbed only covered 4 mile.
Yeah.
And we take the same data from the 4 mile downstream and upstream, and then to see if the reconstruction is something good. Although we don't have the ground truth,
Right.
but it looks okay. So if you take a look at our paper, we have the examples for different locations. And currently we are trying to connecting the same format of data from Virginia to see the pattern. And it can be validated by some vehicle data because it's cheap to send vehicle data to collect some vehicle trajectories to see if it's correct on travel time and something like that. So there is a lot of work to be validate if this idea is really generalizable and what the parameter need to be tuned. But that's a starting point of this problem. So
yeah, no, I guess if you'd allow me a comment was to be like, make sure the kind of technical problem you're working on in the best case scenario can actually be used to solve a practical problem that's traffic management centers or traffic engineers want solved. I think it's there. But
so the application I'm really looking forward to develop is, so this is a reconstruction problem. It don't have the capability to do the prediction. But what if we do in a autoregressive way, then which means you can condition on the last k times and generate the future next step.
okay, that's a different problem, right?
So that it can do the wave prediction. Then the application is that can inform the driver, like be careful to slow down.
I got that for sure.
Yeah.
That makes sense.
Of course, so I mean, I'm just wondering. It looks like you are one of the pioneer for the I-24 data set.
I think I'm just a team member.
Do you remember, but when did you study? You studied when
2022.
the,
So when I arrived, the validation system is in operation.
oh,
Validation system is built up during pandemic. It's a 3-pole and 18 cameras.
okay,
So when I arrived, the construction work I show in the civil engineering part is done,
okay,
but the digital part haven't been tuned on.
nice.
So the first thing I come to the lab and I did, so that time I haven't built up any team trust and so on. The first thing I did is to manually label all the land markers on the freeway.
Right. Remember, we have some discussion somewhere. Yeah.
Yeah, so that you can have the coordination system from the camera back to the real world. So I think I'm not the first person to work on this project, but I experienced from the beginning of the full scale system to now. It's like my role is more on getting the data and trying to formulate the transportation problems and get it done. So
Okay. Cool. So that's I think that's really nice. I believe Jim, is connected to you. So we are using the data set actually. Yeah. Thank you for the great work. And then you're talking about, all these nice waves, but theoretically, they are more like a higher order phenomenon. I'm wondering,
Yeah.
like a first order phenomenon, which is fundamental diagram.
Yes.
Did you guys do any work? I mean, it looks like you show triangle fundamental diagram. So you're a believer of triangular, not gracious?
I didn't, I'm showing that because that's from literature, so.
Yeah, okay, so yes, yeah, okay, let's.
Oh, that's a hard question. I don't have a exact solution to it. But what I believe is that first order model currently cannot reproduce the phenomenon we see here.
Yeah, all
There
this.
have to be some higher order.
The wave speed definitely is the first order.
Yeah,
Yes, LWR is already.
Yes, so if the waves travel at the same time, then LWR can fit.
Mhm.
So I'm actually, I still think I don't have any answer to it, but can the wave be the solution to the PDE problem? I don't know. It's like, it's a
Yeah,
lot
it
of
is.
things.
I mean, the first order.
The first order is the weak solution to the PDE, but what about these kind of thing we see here?
Definitely not the bifurcation or
Yeah.
all those are high order phenomena. But it looks like there's a high consistency, the wave
Yes.
speed, right?
Yes.
That is totally consistent with with LWR
Yes,
with triangular fundamental
Yes.
diagram to predict.
yes.
So that is the question. I mean, did you guys actually try to calibrate the fundamental diagram at all?
Not yet.
That's a very interesting.
So,
Yeah.
It's a very interesting problem, but the data currently has a limitation.
Hmm.
So think about the data is fragmented,
Mhm.
which means you have less travel distance and travel time,
Mhm.
which in return, you will have underestimated density and flow.
Hmm.
We didn't do that because we don't want to deliver something not rigorous. So we want to improve the data quality and then to check the fundamental diagram and higher order terms for PDE and so on.
Interesting. But I think for first order, this data quality should be more than, you mentioned that already, for more than PAMS data. Loop detector data, they should be able to do a really good job
Mhm.
in terms of calibrating.
Yeah.
The fundamental diagram.
I think
It should be triangular, not gracious.
then we need to see. So I think the problem is also, I want to bring this up for discussion, is that the resolution also matters.
Definitely.
So if we do the 1 minute and the 1 mile aggregation, then it can sort of meet the equilibrium assumption. But if you do the very small ED's box,
Mhm.
then is that equilibrium or not? Because fundamental diagram is have an assumption for the equilibrium traffic state.
Exactly.
That's something I still feel confused or I don't have the answer to whether we can fit a curve on the non-equilibrium state. I think that's an open question.
Their idea, by I forgot the Spanish researchers, I forgot their names, and then pick up by Mike Cassidy.
Uh-huh.
He is a near stationary state. By purely using the occupancy and the flow data from the loop detector and show pretty clean pattern.
Okay,
So yeah,
for the
so-
triangular one.
yeah, triangle one, so. Any others?
Can I?
Questions?
Yeah.
So when you calculate the traffic flow and density, those kind of things, so how did you set the size of the eddy domain?
Oh, it's in the box of
Yeah,
the
the-
quantification?
I mean, when you calculate the aggregate traffic flow and density, you need to set the size of the eddy domain, right?
Yes. So
How do you set the?
so all of this work is to generate a speed field. So we make this box as 30 meters and 4 seconds. Actually, that's a very good question. I start to look at the data and I don't know how to determine a proper box size to quantify the traffic measurement. So I write an email to Martin Schreiber. He is a big boss in the traffic data. So he responded with the current suggestion is that if you just want to try to measure the speed, then the box should not just contain one vehicle, but also don't contain 10 plus vehicle.
Contain 10 plus a bit.
So, but for speed, for speed reconstruction or speed measurement, that's his suggestion on that. So I pick up the size of 4 seconds and the 30 meters. But for density, I still don't know, because you can basically generalize the ED's definition can be any shape of the box. So it can be in a diamond shape or even a circle shape, or you just find the stop and go wave and for example, the wave boundaries we detected here can also be a EDS box to quantify things. So I don't have a clear suggestion for density, but for speed, I would suggest to use a somehow.
It should be dependent on like the data frame size, because every eddy domain size, there's the discrepancy between every cells. So if the time frame is too like very accurate. Yeah.
But you can do the moving horizon estimation, right? You can like have the box moving, you can set the sliding window very small, but you can still have some sort of median size of the EDS box.
Okay.
So you mentioned trying to do live detection of crash
Yes.
through the wavefront
Yes.
analysis, and that it was quite unstable because of how, maybe I got this wrong, how narrow the data set that you trained the AI was on. Do you think the stability of those predictions of crash events is a data issue? Need different spaces, different angles of the radar sensors, whatever, in a bigger data set? Or do you think it's a technology problem with the AI model type that you're using?
I think it's okay, I would take it as a cyber-physical system problem. So either something changed on the physical side or changed on the cyber side, which is the data, can make the results bad. So our current working pipeline is that we plug in the real-time data and see what's the problem. And if this problem comes from the sensors, we should coordinate with the sensor team, which like the traffic management vendors, they send people to fix the sensor and bring it back. But the second problem about the technical part is actually hard to answer. But first, we need to create a large data set and select a different subset of the data to test the performance on trend on different set and the value of different things. So I think that's the open problems, and something I'm still working on is like, here is a data set we open sourced called FTAED, the Freeway Traffic Anomaly Detection dataset. That's 1.0 with 4 weeks data. And last November, we actually labeled about 2 years of this data. And then I think that once we wrap it up, it can support the research question you proposed. Actually, that's a very good question.
So do you guys have any plan to extend this to local streets?
Yes. Yes, I think that's more my advisor's job. So they are currently building up arterial testbed with LiDAR.
Okay.
It's like the LiDAR sensor is totally different sensor system. So pick up LiDAR, one thing, it can remove all the privacy from the people. And second, it can work on nighttime. And it can capture the bicycle and the pedestrians. So keep an eye on the new project they are building up. It's called LADEMS, LADDMS, LADEMS. NDOT LADEMS is led by Nashville DOT. It's the phase 1 project that have about 6 intersection with 8 LiDAR sensor. And I think they go through the smart grant phase 2, which will involve 100 LiDAR deployment, about 70 intersections.
70.
Wow. So that you can have a like arterial version of item for motion.
So if we adopt like new system and we need to buy like the traffic sensors, which one do you recommend to install?
I think it depends on the problem you want to solve. So LiDAR is good for 24 hours monitoring and good for nighttime. If you care more about safety, I would recommend to think about LiDAR.
What kind of safety, like?
Pedestrian and yes, more like community scale.
For the purpose, right?
Yes. But for freeway tasks, I think camera is still very helpful because it can tell you what's going on. For example, a tire or dropped on the freeway, then camera can tell you what's the problem, and it can help the TMC people to fix that. And if hand up high enough, you don't have much personal information. But for arterial, you need to hand up not that high, if you hand out camera, it can see everything that block the rule for privacy.
What if we want to focus on like classifying vehicle types? Which one do you think?
I think LiDAR still can do a good job.
Based on the technologies.
Yes, and the LiDAR, those kind of LiDAR company, usually you get a LiDAR, then you get an edge computer. They have some developer tools that already have a classification method embedded in the computer so that you don't have to develop from the beginning. I think more of the traffic application is on top of all the results. So that's what I suggest.
Any further questions?
Yeah.
Maybe one last question before we dismiss, and afterwards, we also encourage you to engage with our speaker. Yeah,
Yeah, we're talking about the last part of your presentation, open source.
Oh, yeah.
So one quick question. You mentioned that like students use AI to read papers. Can you explain more about how students are using AI to read papers?
So what I know is from my experience interacting with undergrad students. So I was like helping my advisor to his class traffic engineering at Vanderbilt, and I was sitting on the back of the classroom. I was like, students are like, if come up on ideas, they will use ChatGPT and so on. And when I help them, especially help them to develop some AI, not AI, some code skills, it's the first thing they come up is to ask AI.
Yeah.
So they are more and more involved in AI. So what we did in the class is actually we encouraged them to use AI. So looks like many undergrad students, especially at the junior level, they don't know many about programming, but with the help of AI, they actually build up some very nice project. For example, one team built up some truck classification algorithm just based on the instruction from AI. But this can actually facilitate them to do better things, as I understand. Like, well, it's not to blame like overuse of AI, but it's to find a better way to use AI to help education and so on. Yeah, that's what I understand.
But as far as the reading goes, I mean, at some point, humans have to gain knowledge.
Yeah.
And the best way we have to do that is to read things.
Yes. So I think what I think transportation research can still do a very nice job in the wave of AI is that our intuition. So people's intuition is priceless. So you come to AI and ask him, like, can you generate a traffic wave? Actually, he cannot. This kind of AI cannot. But people can, people with human knowledge, especially with a lot of observation and experience, can identify what's a problem. Then you can bring in your knowledge and ask AI to fix a line of the bug in your code and make your results better. That's a good use of AI, I think.
Yeah, but I guess my point is like, intuition doesn't come from, fairy dust. Like you have to sit down and read and watch and listen.
Yes.
It's really amazing what, like, have you tried to upload the paper in Gemini and ask for like very specific questions? It's like really able to tell you if that is included in that paper. Like, sure, it cannot read images, but as long as it's written in the conclusions or discussion part and so on, it's really amazing what it does.
Yeah, and I think the future would be beyond the imagination of just asking questions, because AI can actually be your assistant. Like,
Sure, yeah.
do the scientific thing.
Yeah, I've seen some people do it.
Yes.
Thanks for an awesome presentation.
Yeah.
Thank you all.
Right, let's give a round of applause. And so you're dismissed, and you're welcome to engage with Junyi, ask more questions. Ricky, do you have any following events afterwards?